Hey guys, how you doing? I was watching the Facebook groups the other day. Actually, it was today, as a matter of fact, and I was kind of watching all these different discussions that were taking place over a what you would think would be a pretty basic understanding of the operation of OSPF, and I was actually pretty shocked at the differences and the differences of opinions that people had on exactly how the adjacency process works in OSPF. And on top of that, did it utilize just an IP packet, or was it utilizing some sort of TCP connection, and so on? And I was actually pretty shocked about all the different answers that people had. So I thought, you know what, I'm going to go ahead and just build a network. I've got a couple of 2900 series routers here, and I thought I would just go ahead and do a quick video just to describe the OSPF adjacency process and to identify what the packets are, the different packet types that exist, and so on. And I've always told my students in my classes, and I've always told folks online that I interact with, that if you have a question about something, or if you have a misunderstanding, or you don't really understand how something works, the best option that you can always present to yourself from a learning perspective is to go ahead and build it and test it, right? Whether it's in GNS3 or like in my case, I'm using physical boxes I just had sitting around in the office here. But that's really the best way to learn, is to try to discover these things on your own and really try to identify those answers, right? Now, in this question, I think the question specifically on in the process of, on the Facebook group was, hey, does OSPF use TCP in its exchange of messages back and forth between different routers? Whether it's the adjacency process or sending link state advertisements or whatever it might be. And I was really, really shocked about the kinds of responses that I saw there, in that people, were mixed. They said, well, it starts with IP. Some of them mentioned Protocol 89, but then because there's some acknowledgments and there's some connection orientation, then it utilizes TCP and so on. So what I'm going to do in this case is I'm just going to go ahead and I've got two routers connected together. I'm going to set up a very basic OSPF network here. I've actually got, in this particular case, I've got a hub sitting here, and I've actually got my PC sitting on top on this hub, so I can do a real Wireshark capture and capture all the data that's going back and forth between these routers. I've already configured this interface and this interface for basic IP connectivity. I'm going to go ahead and add some IPv6 stuff to this as well, so we can take a look at this in IPv6. But I wanted to show you guys what the real story is here, right? We know that, or maybe you know, maybe you don't know, but there are 5 different packet types that exist in OSPF. You've got your hello packet that we use to exchange our neighbor information and identify neighbors and build those neighbor relationships. You've got your link state request, your link state update. You've got these database descriptor packets, and then you've got your link state acknowledgement. So those are the 5 packet types. I'm going to capture those different packet types and show you guys what those look like in Wireshark, to show you and to answer once and for all this question about whether or not TCP is involved in this communication. And we'll also take a look at some other aspects. Since we're going to look at it anyway, I'll show you some other cool little things here. We know that OSPF routers do go through several different stages to form their adjacency. You've got the down state, you've got the init state, the the two-way state, the exchange state, the exstart state, the exchange state, the loading state, and the full state. So down, init, two-way, exstart, exchange, loading, and full. So I'm hopefully going to be able to demonstrate those different aspects as well. So we're going to do a basic configuration here. I've got Wireshark running. I'll pull that over here in a second, but I want to demonstrate real quickly this process of how this adjacency forms, what the packet types look like, and then hopefully we can put that question to bed once and for all. All right, so let me go ahead and restart my session here on router 1. And I'm just going to do a quick show IP interface brief so you can see that I've got my gig 00 interface operating as 10001. I want to go ahead and set up my loopback interface as well, 172.16.1.1/32. So let me go ahead and go into config mode here. Interface loopback 0, IP address 172.16.1.1. 255, 255, 255, 252. We'll just do 255. I think that's what I had stated I wanted to use on that one. And then I'm going to go ahead and go into router number 2 as well and do the same thing. Do a quick, this session ended here, so give me a second here. Let's get this session going. Let's see, restart session, right there. And I'll just do a quick show IP interface brief on this guy as well. I can ping, excuse me, 10.0.0.2, no problem. You can see those pings work. So we've got connectivity between the routers. Interface loopback 0, IP address. 172.16, and we're going to go ahead and do 2.1 on this side. 2.1 with a 32-bit mask, and we'll do a no shut there. So show IP interface brief. Oops. Now the purpose of this particular discussion is not, I want to try and make this video as concise as possible. So the purpose of this discussion is not to teach you guys how to configure OSPF and how to verify it and troubleshoot it. So I'm not going to really talk too much about that. My goal here really is just to answer that question that was posed online, is what protocol stack are we using? How are these adjacencies formed? What do those different message types look like? So I'm going to go into router number 1. And actually, let me just rename this tab real quick here. Let's see. Let's make that guy R2. I'm going to go into router number 1, and we're going to start the OSPF process by using process ID 1, and I'm just going to take my 10.0.0.0 subnet. Let me do just the entire 10 there, and I'm going to put that guy into area 0, and I'll go into router number 2, router OSPF1, network 10.0.0.0, area 0. Now what should happen in this particular case is I should start to, I should see different packet types coming across. In fact, let me go ahead and pull over my Wireshark here. And sure enough, we see a hello packet here. We see another hello packet here. Notice that those packets are destined for 224.0.0.5. You're going to see some other traffic here, by the way, because my laptop is running a bunch of different applications in the background. So hopefully we can kind of ignore those. But I want to go ahead and create a filter based on the 10.0.0.1 address, just so I can see all of the different packet types that we see coming across. So I see my hello packets. Let me go ahead and stop my capture here. I see my hello packets, I see my database descriptor packets, I see my link state request packet, and then I see a link state acknowledgement packet. So we got 1 packet type, 2 packet types, 3 packet types, 4 packet types, and 5 packet types. All 5 packet types in OSPF right here in our Wireshark capture. Let's start by looking at our OSPF hello packet that was sent to multicast address 224.0.0.5. Now the very first thing that I want you guys to notice, there is no transport layer here. We have our Wireshark information here. We've got our multicast layer 2 information. So we've got a source address of the router's MAC address. and we've got an IP multicast group address, 01005E, which is the standard IPv4 multicast group address. And then the last 24 bits of this address are based on the last 23 bits of the multicast IP address. So it's a layer 2 multicast. There is no transport layer information. And we can tell that actually, by the way, if we look at the protocol field in the IP header. The protocol field in the IP header is supposed to demonstrate to us what the next layer is, or what the next header is. OSPF happens to be protocol 89. So if there was some sort of TCP transaction occurring here, some sort of three-way handshake, that protocol value wouldn't be 89, it would be protocol 6, and then the OSPF traffic would be essentially payload inside of that TCP segment. So just a couple of quick things here. Standard IP header, 20 byte header, DSCP value is marked at 0. Total length field represents the total amount of data that's going to be carried inside the payload plus the size of my IP header. So I'm actually carrying 56 bytes of data inside my OSPF hello packet, because this 20 bytes is included in this 76 bytes. No flags. The time to live is 1. That's actually based, by the way, on the fact that this is a well-known multicast group address. Most of our 224 addresses are going to have a TTL value of 1 because these are link local multicast packets. So we can see that the protocol field is OSPF IGP protocol 89. The source address is the router's interface. The destination address is our well-known OSPF multicast group address. There is another address that's used as well. It's 224.0.0.6, but with 224.0.0.6, we're talking to a designated router. We'll save that discussion for another time. But this is essentially the payload. This is the information that's being exchanged between the routers to allow these routers to form their adjacency. You've got your standard OSPF header. Then you've got your payload. So every single OSPF packet type is going to have this header. Doesn't matter what packet type it is. It could be a link state advertisement, a link state update, but we can see that we're carrying 44 bytes of data. Now, if I break that down, you've got 76 bytes of total length in the IP header, minus the 20 bytes of the IP header itself. That gets you to 56 bytes. And then we've got 44 bytes of packet data here. So this header has a fixed length. We can see that the message type, or what we call the type code, is a 1. That is reserved for OSPF hello packets. The source address is the router ID of the OSPF router. Because I have a loopback interface on the router, that was selected as the router ID for that particular router. And I can see that there's no authentication occurring here. Authentication type is null. OSPF supports plain text as well as MD5 authentication. So this is my standard OSPF packet header. Then I've got the actual hello packet. This is the subnet mask that's configured on the interface that generated the hello. That's going to have to match on both peers. They have to be in a common subnet. The hello interval, which is 10 seconds. The dead interval is automatically calculated at 4 times the hello interval. So this is how often I'm going to be sending out my hello packets. Because my dead interval is a default timer, that's going to be 4 times my hello interval. This is how long I'm going to wait if I don't receive a hello from a neighbor before I decide that that neighbor no longer exists. So we've got some different options here as well. I don't really need to get into the specific options, but this is kind of more of an advanced discussion. It's kind of beyond the scope of what we're trying to accomplish here. Maybe I'll do another video later on that talks about all of the link state options and the different external routing options that we have for OSPF. But we're going to go ahead and leave that alone for right now. This is the router priority that is used for establishing the DR-BDR election process on this multi-access network. 1 is the default, but this is an 8-bit field. We can tell it's an 8-bit field actually, because when I highlight this field here, you can see that it's actually 2 hexadecimal characters here, and each hexadecimal character represents 4 bits. So that's an 8-bit field. This is a 16-bit field. This is a 32-bit field, and so on. So that gives you an idea of how you can look at this hex dump here to see what size of the fields are, and so on. At this point, we haven't actually formed an adjacency. Let's see if our adjacency actually came up here. Let's do a quick show IP OSPF neighbor. Should have. Yeah. Okay. So we formed an adjacency, but in this particular hello packet, I hadn't decided who the DR was or who the BDR was. If I went ahead and started capturing additional hello packets, then I would see some of this information populated as well. And then we've got our LLS data block, which have our type length value fields. This is again kind of beyond the scope of what we're talking about here, but these are TLVs essentially. EIGRP has TLVs, ISIS uses TLVs. All these different protocols use these type length and value fields as like generic containers to carry information about that particular protocol. Type is, what kind of type is this? Is it hex? Is it decimal? I mean, there's a lot of different type representations. The length is the size of the field, and then we can see the actual data carried there. But purpose here, of course, is to prove to the folks online and to demonstrate to the folks online that there is no TCP involved here. All right. Now, granted, this is only our initial communication. This is just our hello packet. So that's what the hello packet looks like. Now, as I go through the process of sending and receiving these hello packets, I'm going through the establishment phase. One of the other types of packets that we'll see is a database descriptor packet. Now notice that this is a unicast packet. So we've already established a two-way state with each other. All of our parameters, our hello parameters and everything, those match. So we know that we can become neighbors. We actually form a two-way state with each other once I see the other router, once I see my, let me try and rephrase this. We form a two-way state once I see my router ID in that other router's neighbor list. And they see their router ID in my neighbor list, which is advertised through the hello packet. Let me see if we can see that in this particular case. We can definitely see that we've got an active neighbor now. So now this, in this packet, I'm only looking at .1. I could go ahead and look at .2 as well. But the bottom line is here is that this is probably at the point when I formed that two-way adjacency because I've seen myself in the neighbor list, right? This is my active neighbor list. So 2.1 shows up in this particular hello. If I was to look at the hello packet from the other side as well, I would see 1.1 listed as well. So that's when we form that two-way adjacency. You'll notice that once that occurred, this is that hello packet. If I came out here and I did a search for 2, I would see similar messages for router number 2 as well. So here is the last hello packet, and what I would expect to see is 1.1 listed here. Once we both identified each other as potential neighbors, we form that two-way adjacency. That's when we start to see these database descriptors being exchanged. All right, so the question is, all right, we've identified each other. We know that we can become neighbors. Now we're going into the X start state. The X start state is where we're doing a DR, BDR election. We're also trying to identify who's going to be responsible for doing the exchange. And we're sending out these database descriptors. Going back to the original point of even recording this video, notice that there still is no transport layer function here. It is unicast communication at this point. It's no longer multicast, but notice that the protocol ID is still 89, so there is no invocation of any kind of transport layer functionality. We still have our standard header. Nothing really changed here. because again, this is the standard header that always shows up whenever you are sending one of those 5 OSPF packet types. We can see that we can identify that there is an MTU size on the interface of 1500 bytes. We've got, again, these different options that we're not going to discuss right now. But then I can see various message types indicating what's happening in this xstart state. I'm initializing the connection. I'm identifying myself as the master potentially. And what's happening in this case, we're not exchanging any routing information. We're just trying to identify who's going to be the chief on the wire. All right. Now those hello packets are still going this entire time, but if I go ahead and walk through these different messages, we can see that we're still exchanging these database descriptors. Now I'm on router number 1, and if I look at my diagram here, it depends on which router started up first, the OSPF process, but this is the router that technically should be the DR. I can find that out if I go into my router and just verify that real quick. Let me go to router 2. Actually, we can see this right here, that router 1 is the BDR. It's the backup designated router. Now that's kind of interesting when you look at this database descriptor packet from router 1, because router 1 is kind of claiming itself to be the master. Now what should happen is eventually it should lose that role as the master. There we go. It lost that role as the master because it identified that there was another router on the link that had was actually identified as the designated router, and that router would be the master. So this is that xstart state. So that's the second phase, right? Now we go to the exchange state. The exchange state is where I'm sending out well, also, by the way, in this xstart state, we're sending out a summary database of our link state database. We don't have any routes in our routing table yet, except for the connected route, but I'll go ahead and add the loopbacks and we'll do some more captures and I'll show you what that looks like. So we go through this link state request process. Notice again here that we're not using any TCP. We're still using protocol 89. These packet types are acknowledged. By the way, out of the 5 packet types that exist, the only 2 that are not acknowledged are hellos and acknowledgements. Link state requests, link state updates, and database descriptor packets do get acknowledged. Because I'm only seeing half of the story here, I'm not seeing all of those different acknowledgements coming back and forth. In fact, let me see if I can go ahead and get the rest of the story here. I'm going to go ahead and apply a filter and do and selected, and then hopefully I can see some of the message types that are going back and forth. I'll also need to specify this as the destination address. Let me see if I can filter out or find some of these acknowledgements. We don't really see them here. I'd have to this data here is my telnet data for my devices. I'll tell you what, we'll look at that in a little bit. But let's go ahead and go back to, I want to complete this discussion here and show you guys the rest of this information about OSPF. In fact, let me just apply a filter based on protocol type here. And actually, I need to do that down here. And let's apply a filter based on protocol type here. That way I can see just all of the transactions going back and forth, hello packets, database descriptors, link state advertisements, and so on. So I'll scroll down here, and we left off on the link state request and the link state update. Let's just wrap this part of the discussion up because I want to show you guys what this looks like in IPv6 as well. The link state update, as I mentioned before, no TCP transactions here. This is an acknowledged packet type, but we're sending out a type 1 LSA. All OSPF routers generate type 1 LSAs to describe the links that they're attached to, right? So we can see the link state ID is 2.1, the advertising router is 2.1, and this is going to be describing essentially that network, that 10.0.0.0 subnet. That's the inside network that the router is attached to. Has a metric of 1 because of the cost calculation within OSPF. What I'll do is I'll start a capture and we'll add the loopbacks to the process here. But before we do that, let's take a look at our request. Also, IP. There is no TCP component to this link state request. And then finally, let's see if we can find an acknowledgement. There we go. Here's a link state acknowledgement. And again, it is protocol. Let me go into the IP. It is protocol 89. There is no TCP component here. So these are the 5 message types. All right. And there's nothing else to it. That's all that exists in OSPF. So hopefully this will put that question to bed as to whether or not OSPF makes use of TCP in any form or function. Now that's not to say that TCP is not going to be used to actually route packets, right? To actually route real packets from clients and from other parts of the network. But as far as the OSPF process goes, absolutely no TCP. All of the connection, the sequencing, the acknowledgements, the reliability mechanisms are built directly into the protocol itself. So let's go ahead and start our capture again. And we'll continue without saving here. I'll go ahead and leave protocol 89 listed here. And let me go back into my Super Putty window. I'll have to reactivate my router 1 session here. I should have changed the console timer or the V2Y timer, but it's all right. So we're going to go do a quick show IP interface brief. And I'm going to do a config-t router OSPF1 network 172.16.1.1 255.255.255. Oh, sorry, let's do it this way. 0.0.0.0 area 0. I'm just going to add that network, and then I'll do the same thing here. Show IP interface brief, config-t router OSPF1, and we'll do network 172.16.2.1 area 0. Oops. It helps if you type it right. Let's do that again. Right here. Nope, not that one. This one right here. All right, so if I do a quick show IP OSPF database router, I should see the 172.16 in there. I do see it, so I know it's part of the OSPF process. And if I go back to my capture, I can see that, hey, I'm sending you an update, which is, by the way, still IP only. There's no TCP component here. And by the way, I'm now advertising this 172.16 network. Now, it is being advertised as a stub network, and that has to do with how OSPF recognizes the network type as a loopback interface. And it's advertising that with a metric of 1 as well. But again, the whole point here is that this is not TCP related information. It's all based on IP packets and OSPF packets. So the last thing that I'm going to do, I'll go ahead and disable OSPF for IPv4. This is annoying me. I'm going to rename this guy. Rename tab, R1. I don't know why, it doesn't really matter, but let me go ahead and get rid of OSPF for IPv4. So config, oh my gosh, come on. Config-t, no router, OSPF1. And I'm going to do IPv6 unicast routing. So I'm going to turn on IPv6. Let me go ahead and do the same thing in router 2. And config-t, no router, OSPF1. So if I do a quick show IP protocols, you can see that I'm not running any routing protocols. And I'll go ahead and turn on IPv6 unicast routing. And then I'm going to do an IPv6 router OSPF1 on this router. and I'll do an IPv6 OSPF, router OSPF1 on this router. We'll do a no, that's fine. We don't have to do that. And then I'm going to go into my interfaces and just turn on IPv6 on my interfaces. So interface loopback 0, IPv6 enable, interface GI00, IPv6 enable. I'm not going to do a full-on IPv6 configuration because that's not really the point here. What I'm doing is I'm basically just enabling IPv6 on the interfaces so that these interfaces can start exchanging OSPF on the particular interface. So interface GI00, IPv6 enable. So if I do a quick show IPv6 interface brief, you can see that my gig 00 interface has a link local address. So that's been established. My PC's going crazy here. It thinks that I'm building this IPv6 network, but we use these link local addresses to actually form our neighbor adjacencies. I'm going to change these so they're easier to read in our Wireshark capture. But let's go into interface GI00. I'm going to do an IPv6 address FE80 : this is router 1, so I'll just do a 1 link local. I'm going to turn on OSPF on this interface in a second. Let me go ahead and go into router 2 and set the link local address on router 2. I'm just doing this because it makes it easier to troubleshoot and read the Wireshark capture. But IPv6 address FE80 : 2 link local. We have to make sure that they're unique. So we've got do show IPv6 interface brief. We've got our link local addresses are going to be much easier to see in our capture. So the last thing I'm going to do is I'm going to enable IPv6. Now, before I do that, let me go ahead and kill my capture here. And I'll restart the capture so that you can see, oops, that's not what I wanted to do. Oh well, that's fine. I'll restart the capture, and the point here is that I want you to be able to see what it is that, how it looks from an IPv6 perspective as well. So let me go ahead and go back into my putty here. Let me close that guy. And I'm going to go ahead and enable IPv6 for OSPF on the interface. IPv6, OSPF 1, area 0. So I'm placing that interface into OSPF. And the same thing here, IPv6, OSPF 1, area 0. Now what should happen is I should see an adjacency form. I don't have term mon turned on here, so let me do that. And I should see an adjacency form on these routers. Show IPv6 OSPF neighbor. All right, we're in the two-way state right now, but we should progress through the two-way state and go into the xstart, the exchange, the loading, and the full. All right. Let me, I forgot to configure an IPv6 address on my PC. Hold on one second here. All right, guys, sorry about that. I had to do a couple of changes in Wireshark to get it to capture my v6 stuff because I didn't have any of my v6 interfaces configured originally. But let's go ahead and take a look. We've got our hello packet here. We can see in this particular case, actually, let me filter again on protocol 89. So what I want you guys to see here is this, I want you to get an understanding that even though we move to IPv6, nothing really changes. Yes, we are establishing adjacencies with link local addresses, and we can see that this is the source address of an OSPF packet, and this is the destination, which is a well-known multicast address for OSPF, just like we saw with 224.0.0.5. But let me quickly just go ahead and shut down. Well, I'll just clear the clear IPv6 OSPF process. That way we can recapture this this process of link state requests and hello packets and database descriptors and all that. I'm going to wrap up this video just by demonstrating that what we just learned about for IPv4 is exactly the same for IPv6. We've got our hello packets, which are protocol 89. There is no TCP component here. They look identical to IPv4 because we use a v4 or a 32-bit router ID. The information in the packet itself, we still have the same router priority or default router priority in IPv6. We still have the same timers in IPv6, but we do see the options are slightly different. We've got some v6 options available now. Designated router, backup designated router, active neighbor, all looks the same. So even in IPv6, we don't use any kind of transport layer for this communication. The hello packet, let's go see if we can find a database descriptor. So here's a database descriptor packet. Again, it's protocol 89. Here is a link state request packet. It's protocol 89. Here is a link state update, which is protocol 89, and so on. So I think you guys get the idea. That is just a quick demonstration of this adjacency process. Now again, the point of this video was not to teach you guys the details of the adjacency process, but whenever I see these discussions online, I feel compelled to kind of go through and, especially if they're as widely discussed as this particular topic, to go through and demonstrate this subject and tell you guys how what this looks like. It's very important, guys, that if you have questions like this, it's great to ask the questions, but I've also noticed that a lot of times online you're not always getting the most honest or truthful information, or certainly the correct information. Just because it's on the internet doesn't mean it's true. So take the time, build it in GNS3, grab your routers from your closet and hook them up and hook up Wireshark and go through the process of looking at it yourself. It's very, very simple. All I did was took a couple of routers, put some IP addresses on an interface, stuck a hub in between, and started doing some Wireshark captures. So hopefully this answers that question, and who knows, maybe I'll record another video here pretty soon if I see another discussion that sparks my interest, all right? Feel free to reach out, ask any questions. I hope you enjoyed the video.